Thank you, Karl-Heinz. Okay, so I'd like to think a bit this morning about how brains think about the world. How do they learn about the physical world in which they're embedded? And I'm going to make an argument and hopefully present some convincing evidence that the best way to address this question we have now is to take sort of garden variety neural networks and make them more neural, sort of add elements of neuroscience, particularly some of the ideas that have been bandied about already. Lateral inhibition is very important, but also top-down feedback and I think synchronous oscillations. But before I get to that, I want to spend a few moments motivating the idea of making neural networks more neural. Why would we want to do that? And I think for many people in this audience, that's a natural thing to do. It's naturally motivated. But I think there are a few of you lurking out there, whether you stand up or not, who probably think that's a waste of time. And I think that notion is illustrated by this headline I dug up on the internet. So, you know, according to some articles, making neural networks more human would actually be a step backward, right? Because neural networks are already better than human beings. So why would we want to debilitate them by making them more neural? So I'm obviously skeptical of that kind of claim. And I think most of you are too. But I was actually at the airport on a long layover in Phoenix on my way to NIPS this year. And I took the following photograph of an object nearby me, just as I saw it. I didn't, center it or frame it. And I uploaded this to Google Images just to see how well Google was really doing on an object detection task. So I'm just curious, how many of you think Google got this right? How many think Google? Okay, now you all know I'm setting you up, so none of you are going to raise your hand. That's fair. Okay, now I'm going to ask it again, but I want you to be honest. Imagine you took that picture and you were uploading it to Google. How many of you now think, would you have expected Google to get it right? Really, none of you are, okay. All right. How many of you, okay, so the rest of you think it would have gotten it right. Do any of you not actually know what that's a picture of? Okay, so I'm going to give humanity 100%, okay, on this image. So let's see what Google did. So Google called that a floor. That was the label, which is not technically incorrect. Top 5, something like that. Okay, but really more disturbing is look at the very visually similar images. I actually just noticed that it says visually similar. Maybe they're sort of cluing us into something. So look at what Google thinks are similar. It's as if Google is using very superficial image statistics to make this comparison. It's just it's not getting any of the semantics of the actual photograph. It's picking up on red things, on gray things, right? But it doesn't look like Google is using semantically abstract features to make this comparison. So that's a little disturbing. Okay, so I'm going to give that round to humanity. Okay, humanity, the score is now humanity 1, Google 0, okay, on who's better at object detection. All right, so let's ramp it up a little bit. Let's go to the ImageNet 2017 results on the video detection challenge. Okay, so this is almost 2 million fully annotated video frames. I'll remind you that this task involves drawing a fairly tight bounding box around all instances of these 30 objects. And these 30 objects are all mobile, so they're either vehicles like cars and bicycles and airplanes, or they're animals like horses and dogs and cats, and there's actually giant panda, one of them. So the point is that this is not, in a sense, I'm also going to give humanity, I'm just going to assert that we're perfect on that. Properly incentivized, we don't make any errors on this. Our error rate would be about something like on the order of the size of the data set, like 1 in 10 to the minus 7 or something like that. Okay, so how well does humanity actually do on this task? Well, it's a hard task, right? I've played with this. Any of you play with this? It's a very hard problem. So I have great respect for the people who compete on this and do as well as they do. But still, the very best algorithm in the world today is still making almost 20% errors. So, if there was a giant panda in a video, you would see it. You would know it. There's no way you're going to miss the giant panda. And I know, and we're assuming you're not counting how many times the basketball players are, okay, all right, you're just looking for giant pandas, okay? You'll see it. So really, there's something amiss here, right? You know, we're told deep learning is better than humans. We see all this hype, but something's not lining up, okay? It's getting 20% errors on a task that, for us, we would be perfect. It is orders and orders and orders of magnitude below human performance. And there's been, so Hava referred to this in her question to Terry yesterday. There was a recent paper from Joe and Bengio, and they've provided some insight into what may be going on. They say that deep neural networks may be, in fact, utilizing superficial image statistics. They're not actually learning abstract features at all. And the way Bengio shows this is he just took these CFAR images, thumbnail images, and filtered them. Just did a low-pass filtering in the Fourier domain. And the point of this filtering is, as far as humans are concerned, it transforms a car into a car. Okay, and he also used also did random filtering. It also transforms, you know, a fire truck into a fire truck, or a bird into a bird, or I don't know what that is. Anyway, but it didn't, whatever it is, it doesn't change it. That's okay. So you would expect if our deep learning algorithms were actually flagging on semantic features, this filtering shouldn't have affected performance very much. It wouldn't have affected human performance very much. But in fact, performance essentially collapses. So the red line is the performance on the holdout data. It's almost 95% correct, which is amazing. That's right at human levels of performance. But do this filtering and performance collapses. There's almost a, what do you call it, 20% performance gap. So what's going on? So, Terry put this picture up yesterday. I put it up here, right? So, I don't know. I think it's somewhat apocryphal, but this book was supposed to have, you know, destroyed the enthusiasm in the first wave of interest in neural networks, and now we're in the, as Dan Hammerstrom terms it, the third wave, and we'll see what effect this paper has. But I think its implications are pretty damning. Even more so, I think we now have some theoretical insight into what deep learning is actually doing, how it actually works. And so I'm referring to this work from Tishby's lab, so where he looks at deep learning in the information plane. And he finds something, I think, that's really pretty extraordinary. I'm just going to play the video that I downloaded from his website, if I can. Play. I've lost my mouse. There we go. Okay, so what he's looking at are the information plane is bits about on the horizontal axis are bits about the data. So there are a lot of bits about the data. There's a lot of data. We have a lot of bits. And in the vertical plane are bits about the labels. We don't have so many of those. And what we're seeing is that as deep learning proceeds as a function of depth in the network, what's happening is that what we're seeing is deep learning is an essentially destructive process. So we were told growing up as learning about deep learning that it was constructive, right? We started with edges, we made corners, we made shapes, we made progressively more abstract features that were more semantic, more general. And in fact, that's not what's going on at all. What deep learning is really doing is destroying information. It's throwing away bits of information progressively through each layer until it's thrown away every last bit about the data that it can and still maintain its decision surfaces. And that's a smart thing to do if your goal is to do really well on holdout data, if your goal is to generalize. But it's exactly the opposite of what biological systems do. We learn everything about the data. We are sponges. We learn about our physical world. We learn constructs. We learn to model our visual world. And then we use that knowledge to solve, to tell the difference between, Andrew and a giant panda, right? I can still do that, even though I know a lot about Andrew. All the knowledge I have about Andrew, where he is, that he's a human, that he's which pixels he actually occupies right now, pub papers. None of that keeps me from distinguishing between Andrew and a giant panda. So I don't have to throw away every bit of information I have about Andrew in order to solve this classification task. All right. So that leads me actually into my talk, but I hope that was some motivation that we need to do something. Deep learning is not working, and it's not working for fundamental reasons. And we need to do something. And maybe it's decision trees or going back to traditional AI. I don't think those are good answers. I think we should look at the brain. And we should look at how the brain is solving this problem and see what are we missing. And I believe the first component of neuroscience that we're absolutely missing in deep learning is lateral inhibition. So what this slide shows is take a garden variety neural network. In this case, this is a convolutional, single-layer convolutional neural network, and just add lateral inhibition between the neurons. If you do just that one thing, and I'll point you to a paper by Chris Rosell in Neural Computation in 2008 for the details, but if you just add lateral inhibition between your neurons, something magical happens. Your neurons, your neural network starts performing Bayesian inference. You start inferring the causes of the data. You're not just slamming a feature vector down on your input, passing it through ReLU. You're actually figuring out what are the essential causes or the true causes of your data. And so this process of lateral inhibition is illustrated or is depicted in this GIF. You can see the neurons kind of competing with each other for the right to represent that image. So if we do this, if we add lateral inhibition and we repurpose our network to just find the causes in the data, we can then train these networks in a completely unsupervised way. We can train them to learn the causes in the data that we can then infer later on particular pieces of data. And so, so this learning algorithm works. You can use a local Hebbian rule. Once you've found a sparse representation for a given piece of data, you just correct your representations with a local Hebbian rule that slightly reduces your reconstruction error given that sparse representation for that piece of data. You do it thousands of times, and you wind up shattering the space into a set of causes. Okay, so that's sparse coding 101. Add lateral inhibition between your neurons and turn your garden variety neural network into a Bayesian inference engine. But is that really a good thing to do? Do I really get anything out of that that makes all that extra computation worth it? So to answer that question, we decided to look at sparse coding of stereo frames, of pairs of stereo frames. The reason we did this was the hypothesis now is that through sparse coding, by adding lateral inhibition, I can infer causes in the data. And in stereo frames, one of the primary causes of structure in the data, we know already, it's depth. So it gives us something to test for, to see if the algorithm is doing what we hope. And so Shen Lundquist, who's actually up the road at Portland State, working with Melanie Mitchell, but at the time he was working with me in Los Alamos, under support from with Dan Hammerstrom's program, Upside program at DARPA. And so what Shen did, so Shen could have started with random weights and just trained it the way I illustrated, but he was impatient. So he actually started with a fast ICA algorithm. So he started with an orthonormal basis that he learned by using fast ICA, and then he took that orthonormal basis and replicated it with a small stride and made a massively overcomplete non-orthonormal basis. And that he fine-tuned using the Hebbian rule with momentum that I showed you in the introductory slide. And in the end, he learns features, and these are just examples of the thousands of features he learned. And you can see they sort of conform to your common sense of what you think the sort of features you ought to learn on this task. So you learn sort of oriented elements that are present with some amount of disparity that varies from element to element. So is this, do we actually learn something about the physics of the world, though? Do we actually learn that the world is three-dimensional? If we did, then the features we infer on stereo pairs should be depth selective. So do we get depth selectivity? So to illustrate that, Shen made this depth map. So he picked a representative neuron. You can see this binocular neuron there's a large disparity between its left and right features. So we expect this neuron to contribute to the explanation of data that's in the foreground. And in fact, when Shen sort of colors in green the pixels that this neuron contributes to the explanation of, they're all in the foreground. So this neuron is in fact depth selective. It doesn't contribute to properly oriented features if they're far away. It only contributes to image components that are in the foreground. So what happens then if we take away the lateral inhibition? We stop doing inference, we turn this back into a garden variety neural network, but it's still using the exact same features, the exact same neuron. It's just not competing anymore with other neurons. Well, all of the depth selectivity disappears. this neuron now responds sort of promiscuously all over the image. Okay, well, Shen worried, well, maybe it's still depth selective if you just only look at the strongest responses. So maybe you can raise the threshold, restore the sparsity, and uncover sort of latent depth selectivity here. So he tried that. So he matched the sparsity by raising the threshold that he got earlier with lateral inhibition. And sure, the responses are sparser, but there's no depth selectivity, right? This neuron still responds all the way, from here back to infinity. So there's something important about lateral inhibition. So what's it? 2 minutes. Okay. So I will just, so this is true for, so it's another neuron that has small disparities in the background. So we extended this idea to stereo video, and we learned features that now not only shift in response to stereo disparity, but also in response to optic flow, although it's not flowing anymore. And so to demonstrate depth selectivity here, I actually took that sparse representation that was trained in a completely unsupervised way and showed that with just a linear regression, I could match the LiDAR ground truth that came from the LiDAR system on top of the car. So yeah, I definitely learned representations that had an implicit knowledge of depth. In fact, my model learned something important about the world. It learned that the world was three-dimensional. And just by adding lateral inhibition between these neurons. And in some sense, this network was trained the way you learn to see, right? You learn to see by just being carried around by your parents, wheeled around the same way, these stereo cameras were carried around on top of this car. You did not learn to see the way we train deep neural networks to see. I'm assuming. Your parents did not, I think, sit you down, in a chair and make you label ImageNet image after ImageNet image. That's not how you learn to see. That would be child abuse, right? So we just learn to see in a completely unsupervised manner just by building models of the data that we're confronted with. And this is, all right, so I'm out of time, so I was going to say something about top-down feedback, but maybe you can catch me at one of the breaks. Maybe I'll slide to one last, just for visual. I just want to leave this impression in your mind. So I was going to say something about synchronous oscillations, but the topic came up last night, why spikes? So this is a model of the retina I spent a long time developing, starting out as a postdoc in David Marshak's lab, and then when I came to Los Alamos. So Terry talked last night about, gamma band oscillations are riding on top of waves of activity that are waves of activity that are spreading across your cortex. Well, they're waves of gamma band activity even in your retina. Your retina is already coordinating the timing of spikes. And there's some beautiful work by all right, sorry, I'm blanking. But anyway, there's a lot of experimental corroboration for this kind of activity in the retina. So I just wanted to leave that in your head. Okay, thanks.
Thank you, Garrett.
Yeah, I'm sorry, Fritz. I just had a panic moment. I apologize. I was looking for you to clue me in, and then I didn't see you there because you were, okay. Anyway, my bad.
So I think I have time for one question. If not, then thank you again. Sorry? There's one. I didn't see that.
So do you think the goal should be to take the framework we already have and essentially have neural networks learn methodology, or do you think it's to take apart the framework and rebuild our idea of neural networks?
Both. Yeah, I think deep learning has been a distraction. It is. I think we're getting, concentrating on classification scores has completely corrupted and misled, the entire community. We need to go back and think about how brains actually learn about the world that they're in. How do they learn the world is three-dimensional, for example? That's kind of important. How do they learn, forget that whether it's a tricycle or, a motorbike or a giant panda. First, we need to know it's a thing. Okay, we first need to actually discover that those pixels group together to be a thing. That's important, like to know those surfaces are part of an object. Mm-hmm. even if we don't have a name for it. So yeah, what Google is doing is trying to completely bypass development. They're trying to do an end run right to the answer, and that won't work. We have to go back and say we have to simulate development. We have to go through that process where biological systems learn about their world, and then we can add whatever task we want.
Yes, I have a question about your very first example, the suitcase in the airport. Yeah. You gave us context. You told us you were traveling, you were in an airport, makes it easy. Did Google have any of that information?
Yes. Google knew I was in an airport. I don't know. Yeah, they actually did. Yeah.
Okay, so I stop here. Thank you.
All right, thanks.